All right.
Okay. Let me just,
Amy?
Yes.
yes, just give me a sec. Okay, so maybe this is a good time to begin. Today we have 3 lectures. One is on somewhat unusual time at 4 p.m. by Mir Parish. So let's make a note of that it's not right after lunch. And okay, so we'll kick off with our second lecture by Randy Hulet on lattice fermions, magnetism, and imbalanced FFLO. And you'll probably, my guess is now Randy's going to switch gears and focus on imbalanced FFLO, his second lecture. Take it away, Randy.
So thank you, Leo. So actually, we'll finish talking about antiferromagnetic order and magnetism today, and probably about halfway through, we'll
Perfect.
switch to FFLO, something like that. All right, good. So like yesterday, please don't hesitate to stop me and slow me down and ask good questions like you've been doing. So we finished talking yesterday about the mod insulator. The mod insulator is characterized by one way to characterize a mod insulator is by its compressibility. And in this experiment, we varied the number of atoms, which directly varies the chemical potential, and we saw how the density responded. And so you can see when the interactions are sufficiently strong and repulsive, the density likes to stay right at 1 per site. This is the Mott gap. Okay, so let's move on and talk about antiferromagnetism. So the way people detect antiferromagnetism in solid state physics is to scatter X-rays or neutrons off of crystals and look at how that scattering at what angle the light is or neutrons are coherently scattered. So the coherent scattering comes about because of this Bragg condition, which is, let's see if I can get my mouse, there it is. So this is the Q is the wave vector of the order. And in our case, Q is pi, 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 which is in XYZ coordinate system, and or sometimes called half, half, half. And you add that coherently with an incoming beam, and you get an outgoing beam at some angle that closes this loop. And so this black lines corresponds to the incoming light. In our case, we're coherently scattering light, not X-rays nor neutrons, but we'll see how in a minute we can make that light scattering spin dependent. So we send in light at this particular angle, Kn, and if it's lined up properly that this loop closes, you get a coherently scattered response at this angle K out. So we have a camera there and we monitor the scattered light intensity. And we also have another camera at some random angle that we call theta. And in theta, it doesn't satisfy this Bragg condition. And so we don't expect to see any coherently scattered light. And rather, it's, if anything's detected, it's diffuse scattering. So the experiment looks like this. This is a stainless steel chamber. In the center of it is this presumed to be antiferromagnetically ordered sample. We send in light that's somewhat near resonance, but far enough away that we minimize spontaneous emission. And we scatter light at this particular angle coherently. And we have a camera waiting to detect that scattered light, and another camera to detect the diffuse scattered light at this random angle. So here are a couple of the angles that correspond to the wavelength of our transition, which is the 2s to 2p transition in lithium is about 670 nanometers. And one can imagine there's 2 types of order in this system, Q commutative order in this system. One is just the crystalline structure itself, the simple cubic lattice, independent of spin. And that occurs at an angle of about 51 degrees, a Bragg scattering angle of 51 degrees on the input beam and on the output beam. There's also the order having to do with anti-ferromagnetism, if it exists, and if it's present in this sample. And that order is defined by, as I mentioned before, pi, 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 or half, half, half. And the angle for that at 671 nanometers is about 57 degrees. So there's a cone here. This is a line that goes down the axis of this cone. And there's an angle on the incoming light, which is 57 degrees. And on the coherently scattered light is at 57 degrees. So I'm going to show the results of scattering at both of these angles and show you that we can use Bragg scattering in atomic physics in the same way that people do Bragg scattering in condensed matter physics to be analogous to X-ray scattering, where we're spin insensitive, or analogous to neutron scattering, where people can detect magnetism because neutrons have a magnetic moment and thus can produce a spin-sensitive Bragg scattering peak. So how do we make the light spin-sensitive? So we make it spin-sensitive by this little cartoon in the bottom, using this idea of having, so we have two levels that we call, as I mentioned before, this upper one is a hyperfine level we call spin down. The lower one is what we call spin up. Now, if you detune halfway in between these two states for your Bragg pulse, you will realize that this upper state has some kind of a phase shift, e to the I pi, relative to the other state, because the dispersive phase is opposite in sign for blue detuning as it is for red detuning. And so by tuning exactly between these two levels, one is sensitive to the spin degree of freedom. So this is an idea that is very powerful, and we'll use it in another context that I'll describe later in the context of FFLO physics. Okay, so this is what the machine looks like in detail. There's various cameras, as I mentioned before, and then there's these beams that are sent in at particular angles. When we designed this machine, we didn't think about putting in beam, viewports at the correct angles. We had to do a little MacGyvering to get these beams in at the correct angles, and we did that by putting in mirrors on these flanges. So this Bragg scattering process of looking at just a crystalline order, at the first example I was showing you on the previous slide, which is an example that's analogous to X-ray scattering. This was done back in the mid-90s by these people at NIST and at Max Planck in Munich and at Wolfgang Ketterle's group at MIT a few years later. So this is what that Bragg scattering looks like. This is the Bragg signal versus lattice depth. Now, if you recall, when you learned about Bragg scattering, there's something called the Debye-Waller factor, which is also sometimes called the Lamb-Dickey regime or Lamb-Dickey factor, which has to do with how tightly confined the electrons or atoms are to their lattice site. So if you're in the deep binding limit, this Debye-Waller factor can be very big. If you're in this limit where the distribution of the electrons or atoms is broad, then that will detract from your signal, and your signal will be exponentially suppressed by that factor. So this data shows the effects of this Debye-Waller factor in the the physics that expresses how tightly confined the atoms are to the lattice site. So this is a function of the lattice depth. The deeper the lattice, the greater the signal, because the Biot-Wallner factor is consequently bigger. This is also showing for the same Bragg angle where we're looking at 001 coherent scattering, or 100 or 010. It's all the same. This shows the angular dependence. So you can see that we're sensitive at about the degree level, which is, has to do with the coherence length in the system, or the size of the system, which is on the order of a few tens of microns. All right, now to detect magnetism, antiferromagnetism in particular, we want to look at a different angle. This corresponds to a lattice vector of pi pi pi, and the angle is therefore at 57 degrees. So we send in light at a 57-degree angle, and we put a camera at the output end where we expect to see coherently scattered light, and we detune our probe, our Bragg probe, to be in between these two spin states. And so to the extent that we can avoid spontaneous emission, this is a way of detecting the spin-sensitive component of the Bragg scattering. So again, we put our camera at these various angles. This one's just used for normalization. This is the one that actually provides the signal. And we send in light from down here, and we see what we got. So this is what's called the spin structure factor. It gives us correlations that alternate. The sign of this alternates every time, every nearest neighbor, every jump along the lattice direction. And this gives a spin structure factor, which has values that range between 1 to n, depending on how coherent the system is. If it's completely coherent, then SFQ will be equal to n, the number of atoms in the system. So it turns out that the Bragg signal is directly proportional to this spin structure factor. So by measuring the intensity of the coherently scattered light, we can measure directly what the spin structure factor is, and that tells us about the degree of ordering in the system. So the normalization is done by looking at that random direction, the q equals theta direction. And we can also look at what the signal is after a long time of flight. Because after a long time of flight, that the Biot-Wallner factor is getting smaller and smaller because the atoms are no longer localized to their lattice sites, and the Bragg scattering signal, and therefore the spin structure factor will diminish as a function of time of flight. So the signal, the spin structure factor, is highly dependent on the density, as shown here in these calculations from quantum Monte Carlo from our collaborators. Each of these colors corresponds to different temperatures. So this is a temperature of about equal to the tunneling rate. This is a temperature which is about 0.4 of the tunneling rate. The signal turns on exponentially because you're collecting larger and larger fraction of the atoms as the correlations build up as you get to lower and lower temperatures. So this is a value of U, the interaction strength relative to T, of about 8. And I think if you remember yesterday, we showed this from quantum Monte Carlo, that somewhere around 8 to 10, U over T, somewhere in the range of 8 to 10 is where the signal should maximize. So this is the kind of signal that we're looking for. This is the proportional to Bragg scattering intensity. So if we get cold enough, we'll see a very large increase, an exponential increase in the signal. So we need to be attentive to the fact that the density, this thing is very highly peaked according to density. So we want the density to be right in the middle of that Mott plateau, to be right in the middle of that, of the Mott gap. So we want the density to be 1. And the way we can vary that is by changing the number of atoms. We maximize our signal by varying the number of atoms such that the density is about 1 per site. We're in this Mott insulating phase.
Randy,
Yes.
can I just ask, is the dependence on temperature is just a Debye-Waller factor?
No, it's the actual order itself. It's not just related to the detection. It's the antiferromagnetic order is itself diminished as temperature increases.
Yeah, that's what I mean. I mean, that's the Debye-Waller factor.
Yeah.
Okay.
Okay.
It's, yeah, okay.
Okay. Any other questions?
And I guess the other one is, do you see secondary peaks as well? How good is the, how non-sinusoidal is the signal that you see secondary peaks, you know, higher harmonics?
Yeah, so we don't see higher harmonics, and partly if we were going to see those, we would see them in the crystalline structure experiment that I showed first, where we're at the 100 vector. We did not see any higher order peaks. One reason is that, well, to be spin sensitive, we have to be detuned halfway between those 2 spin states. And that means that there's going to be spontaneous emission. It's fairly, separation between those spin states is not very big.
I see.
And so we're limited by the spontaneous emission rate.
Okay, thanks.
Yeah.
Randy, can I also ask, the Monte Carlo's calculation include the trap, or these are done for a box, or those include the trapping potential? I mean, this the width of the peak.
So I believe this is a little out of my element, but I believe that they use the LDA.
Okay.
So I believe that the LDA is they've tested that, and they find that it's a good approximation.
Okay. Okay, great.
Yeah.
Thanks.
So this is the spin structure factor, S of Q, as a function of U over T. And as you recall, as I was mentioning earlier, there should be a peak somewhere around U over T of about 10. And indeed there is. So the black filled dots are for the camera at the pi 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 direction, and the open circles is for the camera at the theta direction. And you can see the difference. So the structure factor, this is an absolute scale because we can normalize the signal according to time of flight. And the spin structure factor is easily seen with signal to noise that we have, but it's not very big. So it only goes up to 2. And in fact, that corresponds to a fairly limited range in the correlations of something of the order of a lattice site or so for the range. So in fact, we can compare with quantum Monte Carlo. So these are calculations done by Teresa Paiva, Richard Skolatar, and Asan Kami. And the structure factor increases rapidly, as we saw before, as the temperature goes down. So these are temperatures that range from, I got thing in the way there, but range from about 0.47 normalized to the hopping down to about 1.6. And you can see that it turns on very suddenly. Once you get below about 0.5, which is about where we're at, about 0.51, there's really a pretty good signal. And this is turns out to be an excellent way of doing thermometry in the optical lattice, is to compare these numerical results with the data. And as you can see, the fit is really pretty good over the entire range. And with that, we're very sensitive to temperature. So we can differentiate temperatures between, say, 0.49 to a temperature of 0.54 pretty easily, because this is an absolute scale and not a relative one. So this being able to do thermometry was actually, from a technology perspective, very important, because there had been no good ways of being able to measure temperature in the optical lattice. We didn't really know what it was, other than to be able to turn the lattice on adiabatically and then hold it for a little while and then turn it off adiabatically and see what the temperature was. So this really helps us.
Randy, there is a question about normalization, that if you
Yes.
explain how you are normalizing SQ, and are you normalizing both S pi and S theta using time of flight?
Yeah, so let me back up a little bit.
And what is the effect of the trap for the structure factor?
Yeah, so so the first question is, how do we normalize the signal? So we take the lattice and we simply turn it off. We can turn it off fast compared to the time of flight. We turn off the lattice in a few microseconds. And so we have a signal in the lattice, and we turn off the lattice, the atoms immediately begin to expand. And they begin to expand on distances of order the lattice constant. This destroys the order, destroys the magnetic order in the system. And so eventually you get to a point where, with enough time of flight, you only see the light scattering, the diffuse light scattering from this cloud of atoms, which is unordered. And so you can use that diffuse light scattering to normalize the structure factor, to normalize the signal that we get at zero time of flight to a signal that we have, which is just diffuse scattering at long time of flight. Does that help? And what was the second part, Anna?
It was the effect of the harmonic confinement, the trap for the structure factor.
Yeah. So the harmonic confinement is an issue, and it would be because if you are tuning your conditions, density in particular, to be exactly optimal for detecting the antiferromagnetic order, it means that the volume is relatively small, because it's in this range of the density distribution, which is relatively flat. And I showed you using this compensated lattice technique I showed yesterday, that you can use Bluetooth tuned light, in particular green light, and use that to tune the density and make the potential flatter. You can also make the bands flatter, which also expands the volume of relevance and a volume of interest. But the harmonic confinement and its finite size definitely limits the scope of how big this structure factor can be. Can't be bigger than the number of atoms which is in this antiferromagnetic phase. And so, the more that's limited, the more the signal is limited.
And there are more questions. There is the connection between, is there a straightforward way to see why there is a relationship between the Bragg signal and the spin structure factor?
Yes, but I'm not prepared to show that. I don't have anything to be able to show that calculation. But it turns out, I don't have a way of mathematically proving this to you right now. But it turns out that the Bragg scattering intensity is directly proportional to the spin structure factor. So the larger the spin structure factor is, the greater the intensity of the scattered light. I'm afraid that's as good as I can do.
There are more questions. So is it, how far do the atoms fall vertically during the time of flight, and would this affect normalization?
Yeah, good question. So the time of flight is of order 10 microseconds or so. And in that time, the distance that they fall is, less than a lattice site, maybe something of that order. So that contributes to the time of flight, in fact. So what we want to do in doing this for normalization is to make the time of flight long enough that there's no more order in the system. And so whether they're falling in gravity, which they will, or not, in any case, the time of flight contributes to the diffuse, making the signal, to reduce the signal.
Great. And there is another question: is it possible to distinguish between antiferromagnetic ordering, the Heisenberg model, ground state versus perfect Néel ordering or Néel ordering or order?
Perfect Néel ordering.
Mm-hmm.
Yeah. So if you detected a Bragg scattering signal that was of order n, you would know that you had correlations that were as big as they could be in the system. And so you would have antiferromagnetic order across the entire sample. The entire sample, meaning the sample that had the density of 1.
Mm-hmm.
So yeah.
But I think he's asking between perfect, I mean, that you have singlets in the Heisenberg and just up, down, up, down, up, down in the Néel. So I think that's the question. I mean,
okay, so yeah, so the scattering process that we have projects onto one spin axis, the one spin component, which is along Z, up or down along Z. And if the antiferromagnetic order was not projected into that spin basis, for example, if it was up and down along X, we would have to change. We would have to change the. See, how could we? We would have to do some spin alignment using radio frequency to account for that. And in fact, in our experiment, we worried about that because there is something called canted antiferromagnetism, where it cants out of the plus minus Z basis. And so we in fact did apply radio frequency to transfer atoms that were, say, along X to transfer them to Z, and we saw no effect. So we concluded that the Z basis was a good basis.
So can I add a little more about the Heisenberg, the difference with Heisenberg versus?
Yeah, please.
So if a perfect Néel state, if you just mean up, down, this kind of checkerboard, and you compare that with Heisenberg, they both give a peak in the structure factor that's proportional to n, but the coefficient of the peak is different. So in the Heisenberg or the Hubbard model, the height of that peak is reduced because the spins can fluctuate a little bit. And I forget the numbers, it depends on the spatial dimension, but I think, for example, for the 2D Heisenberg, if I'm remembering right, it's about a 10% reduction of the strength. So surprisingly small, in my opinion. Yeah. So.
But Kaden, just it's good that, like Randy was saying, that for the Heisenberg you can detect it in any ordering, yes, because it's S.S, so it's independent of the ordering, where in the other case it only confined only along a Z direction strictly.
In which case?
In the Heisenberg, because S.S in principle,
yeah. In
order.
which case are you confined to the Z-axis?
If you have a CSC, if you have something that is only SC, an icing type ordering, then in that case, you're going to confine to one direction. So I think if you can check that it's any arbitrary direction, you remain the same, then it's more Heisenberg than icing.
Yeah, but even then there's still a difference between the Heisenberg, so even if you had a perfectly ordered Néel state but was rotationally symmetric, there would still be a difference between that and Heisenberg. Yeah, these are two separate points and both important.
Randy, what dimension are your systems?
It's all three dimensions.
3D, okay.
Yeah, but the basis of spin up and spin down is along what we call the Z-axis. but it's just the basis of the two hyperfine sublevels that we use.
Right, but it's the coupling is Heisenberg, right? It's isotropic.
Yes.
Yes. Yeah, I remember in 2D, it's quite a strong, for 2D square lattice, it's quite strongly suppressed just by quantum fluctuations, even at zero temperature, like something like down to 60% or something like that, the Niel vector.
Yeah, I'll show Marcus Greiner's work in 2D in a moment. Okay, anything else?
I think we are okay.
Okay, good, thank you. So we're here. Okay, so here's a little bit more explanation on the time of flight and how the By-Waller factor is affected by the time of flight, which reduces the signal as the atoms expand. And so, in fact, I should have shown this a little earlier. In fact, if you look at the signal as a function of time of flight, you can see that within about 2 microseconds, the signal decays in this theta equals pi direction. So this also, just for a few details, just to be complete, the lattice depth is about 7 recoils, which give for this theta a U over T of about 13, which corresponded to an S-wave scattering length of about 350 Bohr. So, which is no problem using the Feshbach resonance in lithium-6. Okay. And this is the other direction, and the theta direction, and we won't talk about that much. Okay, so we talked about this slide a little bit. Caden had some observations about this density, critical density to achieve the antiferromagnetic order. This is again the temperature on the vertical axis and the interactions on the horizontal axis. This is the case where the density is homogeneous. And it turns out that according to quantum Monte Carlo, the density per particle is about 0.3 kb in order to enter into the antiferromagnetic regime, but just very, very thin sliver at that entropy. And you have to go below that if you really wanted to get deeply into this phase. Now, the nice thing about this is that if you go in a trap, in a harmonic trap, the situation is really improved. So this is 0.3 still, the blue. And now you can see that you can get entropy maybe a factor of 2 greater and still get about the same degree of antiferromagnetic order. So this is a entropy of about 0.65. And it turns out that our experiment is about on that line, is about 0.65 or maybe a tad less than that, because we can start to see something at U over T of somewhere around 6. So from our thermometry, we know that we're at about 0.5 TN and or 0.5 of T. And that turns out that temperature is just about the Néel transition temperature. So we're seeing the onset of order. We're not yet below the transition, so we're not seeing any long range order in the system. We're seeing just effectively nearest neighbor ordering. We're just not quite cold enough to get very deep into this antiferromagnetic regime. But you can see that there are games that you might be able to play with the density, with the density profile that helps you store entropy out in the wings in this inhomogeneous situation, because the wings are metallic, whereas the core is a antiferromagnetic mod insulator. So this is interesting. You can't necessarily a reservoir, you can't necessarily change the average entropy per particle, but you can redistribute it in such a way that the center part of the distribution can be very low entropy, whereas the edges can be relatively higher entropy. So Caden and I and some of Caden's coworkers and students had thought about this a little bit. One of the things we thought about, I don't know if you remember this, Caden, is putting little punctures of reduced density. So this would be a blue detuned laser beam that pushed some of the atoms out of that region. And this region then be an entropy conduit. It would provide a local metallic region to redistribute and store entropy, but it would also be a way of conducting entropy to the wings where it could be safely stored away from the central region where we are more interested. And we had a lot of ideas on, well, there's various kinds of geometries that one could employ to maximize this, to try to have enough of these conduits that you could very efficiently conduct entropy away from it out to the edges. Well, it turns out in order to make something which is very functional, you had to have a sample which is big enough compared to your optical resolution. Optical resolution in our system is a few microns, and the cloud itself is only about 30 microns. So it's very difficult to do this in any precise way. And we tried doing a single conduit, and maybe we saw an effect on the size of the Bragg signal, but it wasn't clear. So we can't claim that.
So not only have we not forgot this though, but one of our Boulder Summer School students, Eduardo, has acquired all our data and is going to pick that up, very well, Randy. But
yeah, okay, great. So this is a slide from Marcus Greiner, in which he studied the two-dimensional Hubbard model using what's called a quantum gas microscope. And so they're able to, using very high quality optics and very well-designed system, be able to resolve single site ordering, single site resolution in their system. And so with this ability, they're able to also make a reservoir. That's the little thing they're showing down here, and be able to implement the idea that we just discussed in the previous slide. So they made a reservoir on the outside of this. There's an inner region in here that they're interested in. It's something like, I don't know, 10 by 10 sites, something like that. And around that, surrounding that is a reservoir, which sucks away entropy from the center and allows the center to be colder. In fact, they're able to get down about a factor of 2 less than we were. They're at temperatures of 0.25 times the tunneling. We were at temperatures of about 0.5. And by doing that, they could see correlations over multiple sites out to something like 8 sites away, which is about the size of their system. So this is the correlation function for antiferromagnetic order, for the checkerboard order. And this is what their spin structure factor looks like in the XY plane. This is in the pi direction in their case. So let me finish up on this topic, and before we move on to the next one. And this is one example, I think a prominent one, because the Hubbard model has such importance in condensed matter physics. It's one example of quantum simulation of a non-trivial Hamiltonian with ultracold atoms in a lattice. And other examples are the BEC-BCS crossover and spin imbalanced Fermi gases in 3D and 1D. And that is the topic I'll be discussing next. So cooling in the lattice is really important. We talked about the idea of redistributing entropy. We talked about laser cooling directly in the lattice or evaporative cooling directly in the lattice by using a compensated lattice to raise the chemical potential up near the evaporation threshold. So to go to lower temperatures, one has to address the spin degree of freedom, because right now our temperature of about 1.4 times the nail temperature corresponds to an entropy of something like 0.6 or 0.7, which is, log 2, the entropy, total entropy and the spin degree of freedom. So our Mott phase is really low entropy. Given the Mott physics, the double occupancy probability is very small, but we need to be able to address the spin degree of freedom in order to go further. So on thermometry, I mentioned the power of quantum Monte Carlo to be able to do thermometry in the lattice. It works really well, close to half filling, but really challenging away from half filling. And in fact, being able to reproduce our data was an heroic achievement of our collaborators and pretty much pushed the limits of quantum Monte Carlo. And so this is, I think, for thermometry, this is about as far as we could go in terms of comparing with quantum Monte Carlo data. But let me acknowledge the people who did the work. It was Pedro Duarte, Russ Hart, Ernie Yang, and Xinxing Liu, as well as our theoretical collaborators who are invaluable in this work: David Hughes, Nandini Trivedi, Richard Skolatar, Teresa Paiva, and Ehsan Katami. So I think that's it. Yeah. The questions now. This is a little interlude before the next topic. So if you have any questions about antiferromagnetic order or the Hubbard model, this is a great time to ask. If not, we'll push on.
So maybe let me ask Randy very quickly. So what do you think is the future, or how do you envision, or what do you think is in your experiment?
So in our experiment, we're building a new apparatus that has much greater optical access, so greater numerical aperture to be able to write arbitrary potentials onto the sample. So we're using digital micromirror devices and playing around a little bit with those to try to figure out how to best use them and to design this chamber with bigger windows.
Mm-hmm. So you think that you should be able to enter how much you think you can push?
Yeah, so that's really hard to predict, but I do think that one could do a lot better. And these ideas of redistributing the entropy, I think, are still there's still things to look at there, and I think that would be a big advantage in our experiment to have that capability.
Mm-hmm. And the other quick question is, don't you think that looking at dynamics might be easier? I mean, instead of trying to push and cool down to the ground state, could not be easy to prepare any state that and try to see
Right.
some signatures of the, I mean, if you look at the dynamics, you might get some information about the spectrum.
Right. Yeah, it would be great to be able to push down to the ground state and see D-wave superconductivity. That's not an insurmountable goal, but it's a lofty goal, and one which I still think is important and perhaps achievable, but a challenging one. And we need to figure out how to get system colder. To be able to study dynamics and be able to study pseudogap physics and strange metal physics, that kind of thing, I think would be interesting as well. A lot of that is about at the temperatures that we're at, but we don't really have much headroom in that regard, temperature-wise.
Okay.
Okay. All right, good. So let's start got all these things popping up on my screen. I hope that you guys don't see them. Like
Nope, just your slides and your taskbar at the moment. But
okay. So where am I at? I'm here. Okay. Okay, good. So here we are. This is a different experiment and a different group of people involved. In fact, it's an experiment that goes back 15 years in my lab. And there's a long list of names that should be tacked onto here. This is just in the last few years that people have worked on it, but actually, it goes back to 2006. I think it goes back about the same amount of time that Leo's been working on it theoretically. Is that right, Leo? About 2006?
Yeah, something like that.
Yeah.
Well, we started working with Dan Sheehy, not knowing that you guys were doing it, and then discovered that at one of the conferences that you guys were already on it, and that was very exciting.
Yeah. So I've been excited about this topic for a long time, and we've, like I said, we've gone through several experiments studying spin polarized Fermi gases. These are Fermi gases that have an unequal number of spin up and spin down atoms, and looking for this so-called elusive FFLO state. You can hardly say the word FFLO anymore without tacking on an elusive in front of it. So whenever I read about the FFLO state, it always begins by the elusive FFLO state. So there are some examples of FFLO physics, and I'll define what I mean by that. There are some hint of things happening in some solid state materials that have to do with this spin imbalance pairing, but we don't know for sure exactly yet. And there's been a real push in the cold atom community by several of us to try to see a smoking gun signature of this exotic superconducting mechanism. And I think we finally have something that is pretty close. So again, like in the quantum magnetism experiment, we've enjoyed collaborations with Caden and David Hughes, Eric Mueller, and Dan Sheehy, and others. And it's been a real joy in my career to be able to collaborate with these people. And they bring a lot to our experiment. And I think we've been, and I think likewise the other way that we've pushed this field ahead to the point where I think that we're kind of converging on something. Okay, so I showed this slide yesterday, so I'm not going to say much about it other than the focus of this talk today is on exotic superconductors. By exotic, I mean this spin imbalanced FFLO superconducting state. All right, so we're going to go back and revisit some of the experiments that were done, not only in my group, but also in Wolfgang Ketterle's group, and Frederic Chavy at ENS in Paris, and others, John Thomas in 2D, to understand what happens with spin and balance gases in 3 dimensions, but also in 1 dimension. And then more recently, what happens in the crossover when you turn the lattice depth down to such an extent that you couple these tubes together. And what we find is that there's a dimensional crossover, very well-defined dimensional crossover physics that happens at certain values of this tunneling parameter. And we'll also show some new data on FFLO. All right, so as before, we're using these two lowest hyperfine sublevels of lithium as our spin up and spin down system. The spin up and spin down really refers to a nuclear spin. They have exactly the same electronic spin, but their nuclear spins are different, and that's the only thing that differentiates those two states. So what's interesting about those particular states are that interactions are tunable by the so-called Feshbach resonance mechanism. So I want to review that just a little bit. So imagine that you have a way of adjusting the interactions between particles. So you have some kind of a square well interaction between two atoms, and it has some depth U naught. There's no bound states, or let's assume it's shallow for a moment. And I have a two spin state Fermi gas in which I've cooled it down to very low temperatures, well below the Fermi temperature. In the BCS regime, I can form Cooper pairs that are very loosely bound to each other. And in fact, there are many Cooper pairs among the interparticle distance is small compared to the size of the Cooper pairs. And so by adjusting this depth of this potential in some way, and that's what in fact the Feshbach resonance does, I can change this picture by making it deeper. And as I go across this way, I'm making U naught deeper. I make it deep enough that it just supports a bound state. This is what's called the unitarity regime. In the unitarity regime, the S-wave scattering length, A, which really describes the two-body interactions, the elastic scattering, diverges. And so that you can see on this picture below, where the S-wave scattering length shown in red as a function of U naught starts off as negative. That corresponds to an attractive interaction. And when the bound state just appears, its sign of the scattering length discontinuously changes from negative infinity to positive infinity. And as I go deeper still, I form these molecules of spin up and spin down atoms. And so we see that the Cooper pairs continuously change from something which is really big and floppy compared to the interparticle distance to being of the size of the interparticle distance at unitarity to being much smaller, being really bosonic molecules. So you've really gone from something which is a fermionic superfluid to something which is a Bose superfluid simply by changing the depth of this attractive square well. So that's really fascinating. This was something that was pointed out by Tony Leggett 30 years ago, that there was this intimate connection between BCS-like pairing and Bose-Einstein condensation. So you can really think of BCS superconductivity or BCS superfluid as a Bose condensation of pairs. So this is, I think, an important understanding, conceptual understanding that was really provided by our field in this so-called BCS to BCS crossover. So being able to see that crossover depended upon being able to make this potential deeper or varying the depth of that potential so that it's either purely attractive or purely repulsive, or at unitarity where the scattering length is really not defined. So how do we do that? So a Feshbach resonance, yes?
There's a question from Vibhav that says, why is 2D missing from this slide? I think he means 2 slides ago.
Oh,
Or
I haven't,
maybe this slide, the overview. Yeah, exactly.
yeah, because I haven't worked on it. So I'm not going to talk about it. So there's a nice experiment by John Thomas's group on two-dimensional spin imbalance Fermi gases. So I refer you to their work.
Has anyone done 2D pancakes like 1D lattice?
No, not that I'm aware of in terms of spin imbalance.
Right. That's what I mean.
Yeah.
How about Thomas Cole? Thomas, no, Cole, Michael Cole.
Cole?
Mhm.
Michael? Yeah.
I mean, he has 2D, I think.
And 2D spin imbalance.
Mhm.
Okay.
I think, but I don't know if he has
Is
pro
it multiple
FFLO.
layers? Is his just one layer or
One
multiple?
layer. I think it was
Yeah.
only one layer.
Yeah. I mean, also Wasim has one layer in a sort of 2D geometry, although he has another layer.
Right.
Anyway, I was just asking.
In a two-dimensional lattice. Exactly.
Cool.
Okay, good.
Thanks.
So any other questions? Okay. So what we're really considering here is a very fundamental scattering process. So we have, imagine two hydrogen atoms in their ground state, and those two hydrogen atoms are going to interact on some potential. It actually doesn't look too square, but looks more like a Leonard Jones type potential. It has a van der Waals 1/r⁶ tail. And there are two potentials that hydrogen can interact on. This is atomic hydrogen. So those atomic hydrogen can interact on a spin singlet channel or a spin triplet channel. And so it's depending on whether the spins are can be in a triplet state. For example, it could be spin polarized up, or they could be polarized down, or in a singlet state in which the wave function is spin up minus spin down. And S is a good quantum number for the most part. It's approximately good. In most senses, it's very good. And one can do spectroscopy on these two different molecular potentials, and they have bound states. There's a few hundred bound states in the case of the triplet, and a few dozen bound states, or maybe one bound state for the hydrogen. I forget. For the alkalis, it's of order 10 bound states. So because these are different electronic spins, they have a relative magnetic moment. And so one, in fact, can use a magnetic field to tune the energy difference between these two potentials by just Zeeman splitting them. And so, in fact, it's possible to tune a bound state of the singlet channel into resonance with the scattering energy of the incoming atoms. Let's assume the atoms are incoming, they're all of the same spin state, so they're all spin aligned. They come in on this with this scattering energy, and if this detuning is small enough, then there can be a resonance. It could be a resonance scattering process. And in fact, there's a difference between whether this bound state is below the scattering channel or above the scattering channel in terms of the effect on the resonance and the phase shift that is associated with that scattering process. So this coupling between the singlet and triplet channels is affected by the hyperfine interaction. So there's no fine structure in the ground state because there's no orbital angular momentum, but there is hyperfine interaction. There's an I dot S coupling. Because of the I dot S coupling, where I is the nuclear spin, there is a coupling, very weak coupling between these two channels. And it's that weak coupling that gives rise to this Feshbach resonance.
Is there a thermal distribution of scattering energies?
Yes. So the thermal distribution of scattering energies is border whatever the temperature is of the atoms in this in this gas. And we're thinking here of ultra cold atoms. And so the scattering energy might be, in terms of temperature units, might be microkelvin. In terms of frequency units, it's of order 10 kilohertz or so. And these detuning is really big, of order hundreds of megahertz. And so we tune this detuning by applying a big enough magnetic field that that we can change this bound state from below resonance to above resonance. Yeah. Any other questions? Okay. So this is what underlines the Feshbach resonance. So we get to the situation that we had on the previous slide. Let me back up here. We get to this situation where we're at unitarity when the bound state is exactly at threshold or exactly at the collision energy. And there is, because of what you point out, there is a distribution of collision energies. This is a little bit fuzzy, but really on the scale, it's really, really small. It matters the higher partial waves because then we might have a centrifugal barrier. Okay.
I guess the main difference between your two pictures is that here in the Feshbach resonance, you're explaining that the bound state belongs to a different potential. And in the previous slide, it's more kind of a shape resonance, which gives rise to the bound state. Can you comment on that? What is the difference and why is it the same?
Yeah, so this is a simplification. This is just a cartoon picture, and it's not exactly fully correct because of what you point out. It's really a Feshbach resonance involves resonance condition between a bound state of one potential and the scattering energy of another potential. Yeah, that's a very good point.
I would
Okay.
comment.
All the physics could be done next to a shape resonance as well, right? That's what you're saying? It doesn't really change the crossover physics?
Well, the shape resonance would involve some kind of a centrifugal barrier, and you would need to have enough energy to be able to be resonant with a bound state inside the shape resonance, inside the centrifugal barrier. So it really somewhat different. It's a different idea, and it's not tunable. The shape resonance is dependent on the energy of the incoming atoms, and here, because of the magnetic field dependence, it's tunable.
I would just add that the simple potential without a barrier that you had on the first slide where you talked about BCS-BC crossover, at low energies has the same, and low energies, I mean like that's controlled by Fermi energy in these systems. At low energies, it has the same properties as this true Feshbach resonant system that you have on the next slide. So so in terms of scattering amplitude, they're the same at low energies. So in the end, it's this slide that Randy has is the way you realize it in the laboratory and able to tune it, but the first slide is actually captures all the low energy universal physics.
Is that good?
That's
All right,
perfect.
great. So, so here are a couple of experiments done in our lab with lithium-6, in which we studied the BEC-BCS crossover. The magnetic field on the horizontal axis ranges from 600 Gauss to 900 Gauss or so. That is reflective of how wide this Feshbach resonance is. It's hundreds of Gauss wide, and which is really remarkable. Right at 832 Gauss, the the scattering length diverges, goes from plus infinity to minus infinity. And the strongly interacting regime, where defined by the Fermi wave vector times the scattering length being greater than 1, is defined by these vertical lines. And below here, the scattering length is getting smaller and smaller, but remaining positive, and going the other direction, it's getting smaller and smaller, but being negative. So this is the BCS regime, where we have small attractive interaction. This is the BEC regime, where the molecules are weakly interacting, but they are tightly bound by this bound state in the Feshbach resonance. So the experiment we did was to drive a optical transition between the ground state of this gas, whatever it happened to be, if it were a BEC paired gas or a BCS paired gas or something in between, we drive a transition up to a singlet level, which then pulls out the closed channel part of this Feshbach resonance. That's what Z is. And it turns out that Z is proportional to the second order pair correlation function, G2, evaluated at R equals 0. And so it tells us effectively how big the pair is. So these pairs are very small and have a very good overlap in terms of their spatial size is it's small, and small like the molecular size in the ground state. It's small compared to the molecular size in the excited state. So this molecule is maybe 10 angstroms in size, this molecular state that we're driving to. So we have what's called a Frank-Condon factor, which is big for small, tightly bound pairs, and gets smaller and smaller as the size of the pair gets bigger and bigger. And so this is a way of measuring something called the tan contact that was actually measured in Debbie Jin's lab in a very variety of ways here in Boulder, in which she really explored the meaning and significance of this parameter. But it turns out that C is a universal parameter that describes a lot of the low energy ground state physics.
So Randy, there's a question in the chat. Jaron, do you want to unmute yourself?
Sure. I was curious whether you are defining this region back to BCS and the unitarity with the theory or experiment?
This is experiment on this slide. So here we're going right through unitarity. This is where this curves down. This is the location of the Feshbach resonance. And then we emerge out of the strongly interacting regime, and this is now in the BCS regime. So it's what we're showing. One way of interpreting this is that the pairs are getting larger as one goes to higher magnetic field further away from the Feshbach resonance, and their overlap with these small molecules becomes less. And that means that the optical excitation rate becomes less. So this is an experiment. What I showed on this slide and the previous slide were all theory or some cartoon explanations of the underlying mechanism.
Why is there a match in the BCS and also some part of the intermediate regime?
Why is it what?
I'm comparing with this exact dashed line, basically.
Yes. Oh, I see.
I believe the red ones are experiments, right?
Yes. Okay, yeah, thank you for asking that. I forgot to mention that. So this dashed line is just purely two-body physics. So if you don't include the many-body physics of the BCS mechanism, you miss a lot of the physics, because it's clearly not following this two-body exact two-body calculation.
Okay, thanks.
So yeah, that's a very good point. So this was drawn this way to contrast reality, which is given by the experiment, with this very simple model of considering only two-body physics. And clearly the pairs still exist when that bound state is higher than the scattering energy in the Feshbach resonance. But now it's a different mechanism. Instead of forming a real bound state, they're forming some kind of a pair, loosely bound pair. All right, so this is another experiment that we did. So this is an experiment to measure the energy of a superfluid, a ground state superfluid, normalized by the energy of a free Fermi gas. The free Fermi gas has an energy of 3/5 times the Fermi energy, and then times the number of particles. And so this was in the BC limit, and we could measure this by looking at the size of the superfluid core relative to something called the Thomas Fermi radius, which is just the size of the gas in a harmonic potential. And so our data is shown in the purple and blue. And there's a really nice calculation from Martin Zwierlein and Wolfgang Kitterle's lab, which is in red, which is gives the ratio of the chemical potential at unitarity to the non-interacting Fermi gas. That's called the Birch parameter. The Birch parameter, according to MIT's experiment, is 0.376. And according to our experiment shown here by this red dot, it's about 0.39. So they have about an order of magnitude more sensitivity than we do, mainly because they were using a box-like potential and didn't have inhomogeneities to worry about. All right, so this now brings me to the question of what happens when the Fermi energies are mismatched. So the usual situation in a superconductor is that you have Cooper pairs that are completely balanced in the sense that there are no excess spin-up atoms that remain after all the pairs are formed. So this is, and the reason for that is that magnetic fields are excluded from superconductors by the Meissner effect. Superconductors really don't like to have internal magnetic fields, and they'll do whatever they can by creating supercurrents that flow around the superconductor to completely cancel out the intruding magnetic field. So this is the reason why in the Meissner effect there is no magnetic fields found in superconductors. In type 2 superconductors, you can have the situation where at a critical amount of magnetic field, there can be little normal vortices that form in the superconductor that are able to accommodate that magnetic flux. So, normally we have a Fermi surface. Fermi energy of the up spins and the down spins are at the same place. And we have some kind of order parameter, delta, which defines, how strong that attraction is between the electrons in the Cooper pair. But what happens if you apply this magnetic field? Is it still possible to have a superconductor in which there is an internal magnetic field? So this is the case where the spin up and the spin down Fermi energies are no longer the same. So this mismatch can be created by, as I mentioned, magnetizing the superconductor in some way. That can also occur, people have noted, in neutron stars by the quark matter presumed to be existing inside neutron stars. And we can also, using cold atoms, we can very readily realize this situation because there are no magnetic fields, there are no effective magnetic fields that would produce a Meissner effect in a cold atom system. So I guess the challenge that was posed by this system can be addressed using cold atoms with unequal spin populations. All right, so the FFLO superfluid was first proposed by two groups independently, Holda and Farrell in 1964, and Larkin and Ovchinnikov in 1960, well, about the same year, and then it was translated. So roughly about the same time. So again, in the normal BCS system where there's two Fermi surfaces are of the same radius or diameter in 3 dimensions in momentum space, and we have pairing right at the Fermi surface in some width equal to delta in energy units. So the superconducting order parameter defines how thick this this wedge of electrons is around the Fermi surface. So this corresponds to Cooper pairs that are not moving, that they have net zero center of mass momentum. That's the usual situation. Now, in the FFLO situation, if it exists, the mismatch would be accommodated by making pairs with non-zero momentum. So imagine that you boost your downspin atoms in one direction so that they can contact the Fermi surface, the blue one, the Fermi surface of the spin up atoms in one location. And I boost the other direction and they could contact over there as well. So this corresponds to a case where there's a net center of mass momentum Q. The pairs can be formed with a net non-zero center of mass momentum, where Q is the Fermi momentum of the up spins minus the Fermi momentum of the down spins. So in position space, what might that look like? Well, in the LO case, this is the Larkin-Ovchinnikov case, you can imagine accommodating these excess spins in domain walls where the order parameter is spatially varying. So the spatially modulated order parameter gives rise to spatially modulated spin density. And they're at these zeros in the order parameter are places where the excess spin up atoms can reside. And that would be a really strange system. It's kind of a super solid. I think Leo has pointed out that maybe it's not exactly a super solid, depending on your definition of what a super solid is. There's one order parameter and not two. But in any case, there's crystalline order as well as superconducting order in such a system. So does FFLO exist? Well, that remains unanswered to a large part in both theory and experiment. We don't really know the answer to that question quite yet. So we set out to do this experiment. This was something from 2006, where we took real space images of the upspin and the downspin atoms, and we noted that there was a phase separation between them. So this core in the middle is actually unpolarized, has zero polarization, where P here is defined to be the difference in number of particles that are spin up relative to spin down divided by the total number of particles. So this, what we noted was all of these were, there were equal numbers of spin up and spin down atoms in the center. So there was a superfluid, unpolarized superfluid core. And you can see that by looking at the difference between this downspin density and the upspin density, and it's pretty much zero. And really sharp phase boundaries. So there's no evidence of FFLO physics in this, but there was some interesting phase separation. So how much time do I have, actually?
Like 8 minutes. Mhm.
Okay. All right. So let me
Although Randy, maybe we would like to have also time for questions.
exactly.
So feel free. I mean, you can stop when you think it's convenient, and if it's yes, the important part perhaps is to have discussion and
I agree. So before I
We can go a
enter,
little bit into the coffee hour a little bit.
yeah, so before I enter a little into the more detailed section, maybe I should stop here and ask if there are any questions about the concept of FFLO, what it means.
Yeah, I have a question about that.
Yeah.
If the pairs have net momentum, it looks like the average momentum across the surface would be unbalanced. So is this somehow related to a persistent current?
No, that's a great question, but it's resolved by having equal number of pairs going to the left as to the right. And so on net, there's no current.
Yeah, it's like a standing wave versus a plane wave.
I see. So in this picture where the Fermi surface, the green Fermi surface is displaced, that's just a cartoon. That's not real then?
It's a cartoon illustrating that in order to bridge this energy, if I can talk about these in energy space, bridge the energy that's only can only form pairs within a energy range of delta, the order parameter. And so the fact that this difference can be much greater than delta means that one way to circumvent that limitation is that these atoms move to the left or to the right. And that, as Leo says, gives rise to a standing wave. They either move to the left or left going, or move to the right and are right going. So and on net, it's a standing wave and there's no net current.
Well, you can also think of it if there's like two order parameters that couple together, one at delta equals Q and delta equals to minus Q. So it's a superposition of the two pictures. One is the picture that Randy drew, and the other one is the same thing, but shifted to the right.
Mm-hmm.
Oh, what's the FF then? I see it only mentions LO here.
Yeah, so the FF is just plane waves, e to the IQX, e to the minus IQX. Whereas the LO phase is a cosine of QX.
So the FF would be the one where you only have displaced this green one in either left or right and not both.
Yeah, in both cases, you would move the green one to the left and to the right. In one case, they are phased so that they form a standing wave. The other case, they are just plane waves. So the plane waves has no effect on the density, whereas the standing wave does. The spin density can vary.
Am I wrong? But the plane wave case does have a net current, right? So if I had an infinite system,
no, it actually doesn't. It's a little bit subtle. The superfluid component has a net current, but that's exactly compensated by the normal component that's flowing in the other direction. So in fact, the condition for the Q of the shift is exactly so the total net current is zero in both cases. It's just more obvious in an LO where it's a standing wave, but in FF, you need the quasi-particles to backflow to compensate.
Wouldn't that give a net spin current then?
That's a good question. I don't know the answer to that question. Maybe Randy does.
You mean in the FF case?
Yeah.
I suppose that it would, if your description seems to indicate that, doesn't it, Leo?
Yeah, but yeah, I'm just not confident to say because we didn't calculate it, but perhaps
Yeah.
that's
Yeah.
true.
Any other questions?
Maybe I'm going to go ahead. I mean, there have been a lot of dynamical phases of superfluids that have been predicted. I mean, Leo, Victor, of S wave and P wave. Have anyone thought about dynamical phases of FFLO? That you quench one and just quenching and then dynamically it emerges?
Oh, wow. So since nobody's seen FFLO, I don't know of anybody who's conceived of an experiment to study the dynamics. But that would be interesting.
But on the theory
Dynamics might
side,
be easier, right?
yes, exactly,
Yeah.
exactly. On the theory side, have anyone thought? I mean, there has been a lot of studies on the theory, how you really start from something that is not superfluid, you quench, and then you get it emerging at longer
Yeah.
times.
Get
So
a transient.
Maybe this is a cheat, and maybe you're thinking of something deeper where it's purely dynamical. But with my student Yang, we studied quenches of a 1D imbalanced Fermi gas. That's starting with a Hubbard model. And so there you can just quench the parameters into the FFLO state and see it develop and see it oscillate. But, for that, you're assuming that you have a model that realizes FFLO here, you're just quenching into it, as opposed to FFLO emerging purely in a dynamical situation in a system where it would not emerge statically or in equilibrium.
So Lucas has a question I know you'll really like, Randy. Lucas, do you want to unmute yourself?
Yeah. I just was wondering if there are a way to measure a spatially modulated order parameter in experiment.
That's exactly what I'll describe in the remainder of this lecture. Yeah.
Yeah, okay. I guess I have to wait until tomorrow then.
Yeah, I think you have to wait till tomorrow morning.
So Randy, maybe is a sort of taking a step back, and this is connected to when you were talking about Meissner earlier, but can you elaborate a little bit on the difference between, electrons and magnetic fields and your atoms and magnetic fields? They, charge and all?
So, yeah, if you take an electron, you put it in a magnetic field, obviously the electron can change its spin projection, and you can completely align all the electrons in a strong enough magnetic field. And atomic gas, magnetic field has a different effect. We have, Zeeman splitting, which the Zeeman splitting gives rise to the Feshbach resonance, and when you consider two atoms interacting with Zeeman splitting. But there is no way of converting a spin up atom to a spin down atom by applying a magnetic field. So you'd have to do something time dependent. So it has to do with the fact that the states that we consider in cold atom physics are pseudo spin. It's a pseudo spin a half system. It's not really a spin a half system. It's a pseudo spin a half system in the sense that there are two states that can be identified as spin up and spin down somewhat arbitrarily.
And I would say in addition to that, there's because you have charged particles with electrons, they feel a vector potential in their motion, right? And that's what leads to Meissner and gives lots of the difficulties of observing FFLO in solid state systems. But because Randy's particles are neutral, there is none of this coupling to the vector potential in the P minus A squared type way.
Exactly.
So Khosrow has questions. Khosrow, want to go ahead and ask?
Yeah, thank you. So I was wondering, if there's scattering between up and down spins in this picture, and whether the FFLO is actually, does it survive that kind of scattering, or is it a metastable state?
So If it exists, it's possible that it's a ground state. And I'll describe to you some work that people have done theoretically. Leo did some of the earliest examples of phase diagrams in these systems, in which at t equals 0, there is some FFLO physics that is predicted. So it's actually, it's not a metastable state, it's actually a ground state.
Thank you. And also, is the q direction, I mean, this vector q that you defined, is this direction determined spontaneously? And what physical parameters actually determine its magnitude?
Yeah, so that's a great question. So the magnitude is determined just by the imbalance. So it's really a function of the Fermi energies of the two spins, and they're and the imbalance between them. And so the Q is well defined depending upon in a cold atom experiment, depending upon the mismatch in populations of the two spin states. So in that sense, it's not spontaneous. It's something that an experimenter can control. The dimensionality, what direction it's pointing in, is a very important question. And it has to do with the dimensionality of the system. If it's a one-dimensional system, Q can only go to the left or to the right. If it's a three-dimensional system, Q can point in any direction. So there has to be some broken symmetry. Does that make sense?
Yeah, thank you. So, I mean, one thing that I didn't quite understand, I mean, if I may continue with the question.
Sure, please.
Yeah. So, I mean, do you need to actually put the value for the spin imbalance that you need for the FFLO state by hand, or is it, kind of determined by, other parameters that you tune? I mean, like, special kinds of interactions between particles. Do you need to tune it to the actual value that you want, and then disallow any scattering between the two spins?
Yeah, so it depends on whether we're talking about electronic superconductor or a cold atom experiment. If it's a cold atom experiment, we can adjust Q by adjusting the number of spins that are up and the number of spins that are down, and we do that by hand. So we have some mechanism of making a spin polarized gas. It usually has to do with radio frequency transitions between states. But if it's a solid state material, if it's a real superconductor, then it relies on being able to get a magnetic field inside the superconductor that can polarize the gas and thereby create the imbalance in the Fermi surfaces. So one thing I haven't pointed out yet is that this cartoon, although I'm describing it in terms of a three-dimensional Fermi surface, such that these are spheres and not just disks. In 3 dimensions, there'd only be one point where the green Fermi surface contacted the blue Fermi surface. And depending on, if I can move to the left, I can move to the right. So I'd have 2 points in a one dimensional, I have 2 points moving left to right. I have 2 points moving up and down, and 2 points moving in and out of this presentation. So in that sense, there is not very good Fermi surface overlap, and this is a phenomenon called Fermi nesting. And it turns out that in low dimensions, we can completely the Fermi surfaces can be completely overlapped by each other by this kind of a displacement. So in 1 dimension, for some reason to think that FFLO physics would be more favorable in 1D than in 3D because of this so-called Fermi nesting effect. And I'll talk about that in a bit. So what I'm going to do tomorrow, and I'm not going to go further today. What I'm going to talk about tomorrow is to show what happens in 3 dimensions, then do an experiment in 1 dimension. I'll show you the results from that, and then look at the crossover between 1 dimension and 3 dimensions in a bundle of tubes. And it'll turn out, for reasons actually explained by Mira Parrish, one of your lecturers in the summer school. Mira Parrish, back in 2007, when she was a postdoc with David Hughes, pointed out that the 1D, 3D crossover is maybe the ideal place to be looking for FFLO physics. And I think that turned out to be true, as I'll show.
I realize it's a little late. Can I actually ask one more question?
Sure.
So I'm wondering about how much it matters if the momenta that are in your expression for Q are well defined. And I asked that question because I saw that a couple of years ago, there's a solid state group that saw superconductivity in a quasi-crystal that doesn't have translation symmetry. And so the momenta, at least lattice momentum, is not well defined. And so is it just the case that you get FFLO if you have some kind of unpaired electrons, and like you don't really need to have any well-defined momenta that, follow this expression, Q equals the difference in K? This is also kind of a weird question, so I'm happy to not have an answer now. But
are you thinking of like a spin density wave or pair density wave, something like that?
I don't know. I just know that, people saw superconductivity in a quasi-crystal that has Penrose tiling, and they mentioned that it looks like FFLO superconductivity. It has this spatially modulated order parameter thing.
Yeah.
But if you're saying that is related to Q equals, K up minus K down, then I'm a little confused by that, because in quasi-crystals, you don't have well-defined K.
Yeah. So there are things called pair density waves, in which they have finite momentum pairs, but those are related to some kind of underlying length scale of the lattice, or whatever else it defines the length scales in the system. In the FFLO, the Q is defined entirely by a magnetic field. That there's some kind of a magnetic field inside the superconductor in which lists the degeneracy of these Fermi surfaces. So that's kind of a definition of FFLO. As a consequence of that, it gives rise to this finite momentum pairing. The finite momentum pairing, I think, can show up in other systems as well. Am I right, Leo?
Yeah, I mean, spin orbit coupled superfluids. And actually, I will talk about, if I get to it, like from P wave from P wave, you can also get finite momentum. But just as a comment, I would say, for pair density wave, there's commensurate ones that have to do with the lattice. The length scale is commensurate with the lattice scale, but there's also a more general one, which is incommensurate one. Then it has nothing to do with the lattice. And in that sense, the incommensurate pair density wave, in some sense, is even more exotic than the FFLO, because FFLO, you're creating a length scale with the magnetic field by mismatching the Fermi surfaces, the delta KF, you created that length scale. In incommensurate pair density waves, that length scale is purely dynamically, comes purely from interactions.
Has that been seen?
Well, depending who you ask, there's no smoking gun for sure. People argue about it all the time in the high TC contexts. People like Patrick Lee and Kivelson, and then there's experimentalists Seamus Davis and that argue for it, as both experimental theory and numerical evidence. But I think the jury is still out, I would say.
So I hate to cut off the discussion, but we are getting pretty deep into the coffee time. So I don't know if people want to take a break, and if you want to get on GatherTown, go and continue discussion there. But we should have a break for 20 minutes or something, right?
Also, I'll say that I put a couple of references, longish references, detailed description of many of these issues that people interested, they can follow up.
All right, thanks, Leo. So I look forward to seeing everybody tomorrow morning.
Thank you, Randy. Thank you for the fantastic lecture.
My
Bye-bye.
pleasure. Bye.
Thank you.
So I'm going to stop the Zoom and we're going to resume